Okay, so that just inspires people to go beyond. So in the mid-1980s, single ions were detected in vacuum and electromagnetic traps. Single atoms were studied with scanning tunneling microscopy on a surface. But what about molecules? People thought it was impossible, of course. So I want to tell you how we came to the point of detecting a single molecule. So we need a little spectroscopy now. Think of a molecule like pterylene shown here, highly conjugated aromatic hydrocarbon. And if you put the molecule in a transparent host of peritofenil, then measure its spectrum at room temperature, its optical absorption spectrum, or UV-Vis, you see the lowest electronic transition on the right, and then some vibronic progression. So broad at room temperature, as you know. But when you cool this to low temperatures, 2 degrees Kelvin, then that first electronic transition gets very narrow, so narrow that you can see 4 inequivalent sites in the host crystal. And so now let's think about just one of those very narrow lines. It turns out it's filled with many, many more tiny narrow lines coming from the individual molecules, but you can't see them here. So in those days, I was at IBM Research in California, San Jose, California. And we were using this kind of a spectral line at low temperatures, the kind that I just showed you there on the right. That kind of spectral line is going to be useful because it can allow something called frequency domain optical storage. The idea was to store bits of data in that line by marking different colors or different wavelengths using a laser and changing the absorption of the molecules, a method called spectral hole burning. And this actually utilized the fact that these were inhomogeneously broadened lines of zero phonon transitions. And much great early work, foundational work, was done by Roman Parsanov in Moscow and also Karl Rabane in Estonia. And so this work relied on this inhomogeneous broadening. But at that time, I was working at this great industrial research lab. And the nice part about it is that we not only were thinking about certain technologies, but we could also do the science underlying the technology. So in this case, the critical step was asking a question about these inhomogeneously broadened lines. So here's that inhomogeneously broadened line again, just like the one I showed you on the previous slide. Now we're spreading it out a little bit more. And the question is it smooth? Is it smooth like it's shown here? Now switching to penincin and peritofenil. No one had looked closely to see if it was truly smooth. So we looked to see, and we saw this. We saw this amazing structure, which we called statistical fine structure. And this statistical fine structure is coming from the fact that at each wavelength, there are different numbers of molecules piling up at that wavelength. And they're never going to be exactly uniform because of number fluctuation, square root of n effects. So, sorry about that. So this statistical fine structure showed us, we can see something that depends upon the number of molecules, actually the square root of the number of molecules. And that's my postdoc at the time, Tom Carter. So the idea here was, we've observed some strange new effect, and in fact, it's coming from the molecules and their individuality. Why don't we try to go see and detect a single molecule? So that's what happened in 1989, now 30 years ago. So this is another big anniversary for us. We detected the optical absorption of penincin in peritofenil at low temperatures. That's with my postdoc Lothar Kador. And it was done with quantum-limited laser frequency modulation spectroscopy, this fancy technique. But it worked to observe and open up the field. A year later, Mishel Ari did a very important experiment. He also detected the absorption of a single molecule of penincin in peritofenil, but he used a slightly different detection. He detected the fluorescence emitted from the molecule as it was absorbing light. So that's an important step forward. So at this point, what have we got? We've got a low temperature, very high resolution, seemingly very esoteric thing, detecting a single molecule. A wonderful scientific advance, many scientific effects, but some people might have thought, well, who cares? Why did you want to detect these single molecules? So the first reason is surprises start to occur. On the left, you're going to see many spectral scans over a little spectral range. And then you will see, hopefully, if something goes wrong, where is it? It should be there. It's not starting. That's too bad. Let's try one more time. It worked briefly during the testing period. All right. Anyway, what we observed is that a few individual molecules, instead of sitting at one frequency, they would start jumping around from one frequency to another in a stochastic sort of way. And if you fix the laser at a fixed frequency, then you see that the molecule is in resonance, out of resonance, in resonance, out of resonance. It's like it's blinking on and off, turning on and off in a random sort of way. Again, people thought, well, this is not very interesting, but maybe we'll have some application later. The other thing that we were able to observe is that you could use light to move the molecules around. You can have a single molecule sitting there at one frequency and then irradiate it and it disappears and then wait a little while and it comes back again. So we were able to use light to control the molecules, another interesting effect. The message in this part of my talk is that even in an industrial research environment, when the exploration of technology includes a passion to explore fundamental basic science, important discoveries can occur. So now, the next question that you might be wondering about, well, why do this? Who cares? Why should you study a single molecule? So let me try to illustrate the answer, which is, we don't then have to measure only averages. Remember, all previous experiments before single molecules were averaging over millions and quadrillions and billions of molecules at the same time when you do a measurement. Now you can measure one at a time and measure it, and see if they're all the same or if they're different. The analogy here is a sort of a simple one. Think about this picture of Berlin from far away, and you're trying to observe cars, so you try to look closer. And now, yes, you know there's cars on those streets, but you're now measuring the average. You're not seeing any individual cars. You try to get closer. It's still pretty much averaged, and you cannot see what's really happening. But if you have a method of seeing the individual cars, then you see that some are stopped, some are moving, some are maybe turning, some are doing different things. And this is the kind of thing that can happen when you can observe individuals instead of just the averages. So that's why we do this.